I often get questions about how do I set up an ICE table. So here's an example that uses one. So note that an ICE table is not magic. It's a problem-solving tool that is best used to organize information about chemical equilibrium and to apply the law of mass action. So what that means is if you have initial amounts of something in a reaction and you have equilibrium amounts and you have an equilibrium constant, the ICE table helps you put those things together. So in this question, we are told that a reaction container is filled with 3 atmospheres of H2 and 2 atmospheres of I2. The system is allowed to reach equilibrium, and so if Kp equals 100 at this temperature for this reaction, what is the equilibrium partial pressure of Hi? So we're trying to find, from this question, we're trying to find what is the equilibrium partial pressure of one of the components. And we're given initial or not equilibrium amounts. So those are here. We also have the chemical reaction and the value of K for this reaction. So to organize that information, you should set up this table. Your table should look like this, where on the top row you have the reaction. So sometimes these are called Rice tables because you have reaction, initial, change, and equilibrium. So you have a column for each of the components in your reaction. So here, the 2 reactants, H2 and I2, and then we'll kind of put our equilibrium arrows here. Those are going to form 2 equivalents of hydrogen iodide. Initial here means at the beginning of the reaction, so before the reaction has reached equilibrium. We can get from our problem the initial amounts because it tells us that the reaction container is filled with these things. So we'll enter in here those initial amounts that we have, 3 atmospheres of H2 and 2 atmospheres of I2. We don't know how much HI we have at the beginning of the reaction because the problem statement doesn't say anything about that. But because of the sort of context of this problem, we are going to infer that we have 0 atmospheres of HI at the beginning. Now, change means how much each component will react. In reactions that go to completion, we know how much changes based on the limiting reactant, and we can use stoichiometry. But here we don't know how much will change because it depends on the particular amounts that we have and the value of the equilibrium constant K. But we do know that the changes between the reactants will be governed by stoichiometry. So I will set the total reaction change equal to X, and then know that each component will change by its stoichiometric coefficient times X. I also have to determine which direction the reaction will proceed to get to equilibrium. And so I can calculate the reaction quotient Q. Here, I see that the reaction has to proceed in the forward direction because I have 0 products, so I can't have any less than that. So that means that my reactants will decrease. So H2 and I2 will decrease by X, and HI will be formed in an amount equal to 2X. And again, the 2 is from the stoichiometric coefficient of 2 in front of the I, the HI. Okay, so now initial, we sort of add down here. Initial plus change is going to equal the equilibrium amount. So we're going to drop some significant figures here just to make it easier to write. But that means that the equilibrium amount of H2 will be the 3 we started with minus however much we lose to X. And so I2 will be 2X, and the equilibrium amount of HI will be 2 times X. Okay, so now we need to solve for X. I know that at equilibrium, the ratio of the products to the reactants will follow the law of mass action. Okay, so I know that this ratio will equal 100 at this unspecified temperature. And so I also know that those equilibrium partial pressures are equal to the values in the equilibrium row of my ICE table. So I'll substitute those numbers in. So I see that the partial pressure of HI is 2x. I'll square that value because in the equilibrium constant expression, the partial pressures are raised to their stoichiometric coefficients. And then in the denominator, I have the partial pressure of H2 at equilibrium and the partial pressure of I2 at equilibrium. And I know that all of that will equal the value of 100. So now I have an equation in one variable, and now I can solve for x with algebra. If I do that, I will get a quadratic equation. So if I rearrange here, I'll get 96x squared minus 500x plus 600 equals 0. And I will find that my two roots for this are 1.875 and 3.33. Now, a quadratic equation produces two roots, but only one of them is chemically reasonable. We see here that this first one, 1.875, is the only one that would make sense. Because if, for example, if we looked at the H2, if x were 3.33, we would do 3 minus 3.33, and that would be a negative partial pressure, which is chemically impossible. Okay, so now we've solved for x, which equals 1.875. If we go back to the problem statement, we see that the question is, what is the equilibrium partial pressure of HI? So we see that the equilibrium partial pressure of HI is equal to 2 times x. And so we know that the equilibrium partial pressure will then be 3.75 because that is 2 times x.